Hello everyone, in this video I'm going to give a brief introduction on Wilkinson power divider. It is also called Wilkinson's power combiner. So to begin with, let's take a look in the most basic form. You can purchase this device very easily. It doesn't cost a lot. It's a device with 3 ports, and connecting port 1 and port 2 is a quarter wave transformer with characteristic impedance QZ, and connecting port 1 and port 3 is another identical quarter wave transformer. And more importantly, connecting between port 2 and port 3 has a resistance here. The value is 2 times Z0. Without this resistance, whatever reflected power in port 3, whatever reflected power is in port 3, it will go through this pathway and then eventually it will hit back. It will hit port 2. So in other words, there is no isolation between port 2 and port 3. But with this resistor here, whatever reflected power you have in port 2 or port 3, it will be consumed by this resistor. So first, all the port is expected to match with a match impedance, Z0. The power can be either fed from port 1 and then delivered to port 2 and port 3 equally. In this case, you are using the Wilkinson power divider as a power divider. Alternatively, you can also feed the power from port 2 and port 3. In this case, you are using the device as a Wilkinson power combiner, and the output will be in port 1, and the amount of the power that you have in port 1 will be the combined power of port 2 and port 3. There will be some loss depending on the match condition. If there is any unmatched, then there will be loss. If there is a perfectly matched port, then there shouldn't be any current through this resistor, and you will expect some power loss because of this refraction, because of this quarter wave transformer. But you get a combined power. And before moving forward, let's take a look in this device. The output port 1 is delivering power to 2 transmission lines, 2 quarter wave transformers. In this case, for the sake of analysis, it's typical without any modification. What we can do is we can split the port 1 into 2 parallel components, parallel resistor connected to the ground, and each of the resistance of each of the resistors is 2 Z0. So the parallel network here over a overall impedance Z0. So basically you have a, on the other hand, you will take a look in resistor connecting port 2 and port 3. The overall value is 2V0, and you can easily divide it into two individual resistors connected in series, and the resistance of this resistor, of any of this resistor, is Z0. So what happens in even mode? Even mode occurs when both port 2 and port 3 have the same voltage. So this is what is, both sources are V of S. Under this condition, because the voltage at port 2 and port 3 are identical, then the voltage at port C and D will be identical as well, and the voltages at port node A and node B will be identical. If the voltage between if the voltage at C is exactly the same as the voltage at D, there will be low current going through this resistor. In this case, you can consider this resistor as you can treat this resistor. This resistor can be affirmed to be non-existent because there is no current. This means open circuit. Same here, you have a conducting wire connected to A and B. But because of the absence of any current, if A and B have the same voltage, then you can assume there is no wire connecting here. This is so-called even mode. C and D are equal, then there is no, so there are open circuits here, open circuits here. So for the purpose of even mode analysis, the equivalent circuits can be drawn in this manner. You cut off in the middle line, and under this condition, the characteristic impedance of this quarter wave transformer can be calculated. With the left side to Z0 and the right side is Z0, and square root of them, then the result is square root of 2 times V0. So this is the idea. But ultimately, we want to know the S parameter of a Wilkinson power divider. So we don't just start here. We will use the even mode analysis to work out the even mode voltage at each plot. And this is what we are trying to do now. So this is one of the branches. The other branch is the lower ones. It will be identical with this. And this wire is useless. And this resistance is also useless as far as even mode is concerned, because there is open circuit. Now, basically, you are having a circuit with resistor connected in series with the quarter wave transformer and the input impedance at port 1, where the impedance has a resistance 2Z0. So under this condition, you may wonder how we can solve this problem. The easiest thing I suggest is to work out the input impedance towards the right end of the quarter wave transformer. You know what to do, yeah? So the y-end of the transformer has a input impedance. Calculate in this manner. Square of the characteristic impedance divided by the load. The load is 2V0. The characteristic impedance is square root of 2V. And as a result, you got exactly V. So, interesting, right? This resistor is useless, but on the other hand, the input impedance at port C, at node C is exactly V0. So in this case, you don't need to tell right the even more voltage at port 2 has to be using the voltage divider technique, right? It has to be equals to the source voltage divided by 2. Vs divided by 2. Now, we know the voltage at port 2, but how about the voltage at port 1? I'm sorry to tell you, there's no straightforward answer. There's no straightforward. The answer is very straightforward, but the method to derive it is super complicated. You need to use the S-Palatum ether matrix for quarter wave transformer. And before doing this, let's work out the reflection coefficient, looking into the right end of the transmission line. Of the quarter wave transformer. So you can calculate this at port 2. The incident voltage of given mode is equal to the reflection coefficient times the refractive voltage. I'm now talking about the low refraction. I think I need to solve it. Hang on a minute. This one should be minus. Okay, now going back here, the reflection coefficient is given by the low impedance minus the characteristic impedance divided by the low impedance plus the characteristic impedance. So I reverse it because of this equation. Because we are now looking into the port here, the right end of the transmission line. Now let's continue. The S parameter for the quarter wave transformer is that simple. The diagonal is 0 and all other element is -3. So what you need to do is you construct a system of equations relating the voltages for port 1 and port 2. Incident and refractive voltages for port 1 and port 2 using the S parameters. This is what you get. And now you are going to extract all the rows here and rewrite each of the rows in equations. So this is what we get. The first row can be related with this equation. The second row, we do a little bit of algebra. We move the -3 to the left, and then this is what we get. And remember, the incident voltage can be rewritten as the reflected voltage times the incident voltage. And now we can continue with our analysis. Even though the port 1 is equal to the sum of the incident voltage at port 1 and the reflected voltage at port 1. But the incident voltage can be calculated according to the first equation here. It can be substitute with this. And then the next thing is you will write the incident voltage can be rewritten in this. You can substitute to here. And the reflected voltage can be written in this manner. So as a result, you can simplify this equation. And fortunately, in the previous page, we have already calculated the incident voltage at port 2. Is that one? Okay, the incident voltage at port 2 is equal to this one after some calculation we get this, but the incident voltage at port 2 it can be calculated in this manner. Is equal to 1 divided by the reflection coefficient. Because of the reflection coefficient, then the voltage is different. Okay, now we can move on, and you will substitute the reflected coefficient with this one, and you resolve it. You will end up with a very clean formula. The voltage at port 1 is exactly equal to minus 3 times square root of 2 times this one. And this is the way how you relate the voltage between port 1 and port 2. Because the source voltage at the even small source voltage at port 2 is Vs divided by 2. So you can just substitute to this equation to get the final result, and you discover the even more voltage at port 1 is equal to minus 3 times V of S divided by square root of 2. And this is quite clean. Now you are looking at port almost. Almost is very, very simple. Now you go back, let us go back to the first page. So what is almost? Almost is when port 2 and port 3 are connected with a different voltages. The magnitude is the same, but the signs are different, and this is so-called port mode. Because of the difference between the voltage at the upper port and the lower port, you will expect a current going through this point. So we'll go back to where we were. So this is the way how we analyze it. Remember, in electronics, when we analyze the differential amplifier, we use the midpoint. We treat the midpoint as a virtual ground. This virtual ground is the same ground as the AC ground, but it doesn't conduct at DC. Same here. This is the virtual ground. We can use the midpoint as a virtual ground. In this case, we cut off and then the upper branch will look like this. So here we have a connected connecting port 2 to the ground is a resistor with resistance 0. And on the other hand, at port 1 is connected straight to the ground. So if this is the ground, there will be no voltage in AC sense. So same for the lower branch of the Wilkinson power divider. But however, the voltage driving the lower branch of the Wilkinson power divider is minus JS instead of, so minus V of S instead of V of S. Almost happens when the voltage sources for port 2 and port 3 are opposites inside. So this is what I'm telling you. Under the almost condition, there will be current flowing from node C to node D and node A to node B. Under the almost condition, these nodes will carry 0 volts. So there will be no refraction. You cannot say there will be another refracted incident voltage. You may just assume it's 0. The main reason is all the voltage here will go straight to the resistance here. All the power will go straight to the resistance here. The input impedance towards the right end becomes, you can use the formula to calculate the input impedance at the right end of the quarter wave transformer. Is equal to the characteristic impedance square divided by the low impedance. The low impedance is 0 because you are now connecting the circuit in this manner. So you can just forget about this resistance. There will be no current going through this resistance in almost. So by calculation, something divided by 0 is definitely infinity. So you can just assume the left part of node C is completely non-existent. Hence, if the left part of the node C is non-existent, then the circuit is voltage V of S connected to Z0 and connected to another Z0. So obviously, the voltage here has to be V of S divided by 2. So here we are. Now at port C, at port 3, we are going to go through the similar analysis. But one thing, I should say, the source voltage will be minus V of S divided by 2. But the S parameter for port 3, between port 1 and port 3, will be the same as the S parameter between port 1 and port 2. They are both identical anyway. The only difference are the voltages. This driving voltage on the upper branch is V of S in almost, and the driving voltage in almost for the lower branch is minus V of S. This is the only tricky part. Okay, we will continue with our analysis. Our interest is in the optimal voltages at port 1 and port 2. Port 1 is very simple. First, we take a look in port 2 first. There is no transmission line because the input impedance at the right end of the quarter wave transformer is infinity. So virtually there will be no transmission lines involved at the right end. At port 2. So I connect, let me just correct it. Let me correct it. At port 2. With no transmission line, all the current will go through the resistor and then straight to the ground. The resistance of the resistor is 0. So with this in mind, then the incident voltage at port 2 is still V of S divided by 2, but there will be no refractor voltage at port 2. So now we are in the position of combining the even mode and odd modes together and then find out the S parameter. At port 1 is the sum of the even mode and odd mode voltage for port 1. The odd mode is 0. The even mode voltage is the J times V of S and then times minus 1 divided by square root of 2. So this is that symbol. For port 2, again we combine the even mode and odd modes together to get the answer. Both even mode and odd modes has a value of half of the source voltage, V of S. And as a result, you can say the voltage at port 2 is V of S. But there will be no reflection under the matched condition. There will be no refractor voltage at port 2. So you may assume all the voltage are incident voltage. So now we are going to derive the S parameter. At port 1, the refractor voltage is that much because under the matched condition, you shouldn't expect any wave. When you use the power divider as a power combiner, then there will be no incident voltage at port 1. Only all the power will be combined and delivered. This is the expectation of an ideal Wilkinson power divider. For port 2, we expect all the voltage to be incident to each of the ports. There will be no refractor voltage. As I said here, there will be no refractor voltage, all the source voltage become this. So let's calculate the S parameter. S12 is a refractor voltage at port 1 divided by the incident voltage at port 2. And as a result, we get this. Because the network itself is a passive network, it's reciprocal as well. So if you can calculate S12 is equal to this amount, then S21 will be exactly the same. Unless you have active element in the circuit, otherwise it will be the same. This is the law of reciprocity. Since port 2 and port 3 are symmetrical in nature, so if we have S12 equals to this amount, S13 will be the same. And again, To follow the law of reciprocity, S1 free will be equal to SP1. Okay, dividing the S parameter. For port 2 and port 3, you might wonder what the S parameter will look like. Because in even mode and almost, there will be low reflection at port 2. There will be low reflection at port 3 either. So, with this in mind, the S21, S23 has to be 0. And this is the beauty of the circuit. By virtue of reciprocity, right, S23 should be equal to SP2. So there will be a complete isolation if the impedance are well matched at port 2 and port 3. Since the Wilkinson power divider is designed for matching all the ports, so you can expect the diagonal is of the S parameter matrix is all 0. So this is what we get. And this is what we get. This is the S parameter matrix for the S Wilkinson power divider. Okay, now let's take a look how we can implement this in number elements. To implement it in number element, we need to convert the quarter wave transformer into a pi level or even a ladder structure. The whole idea is to replace the quarter wave transformer into pi level, or equally you can make it Y bound, by having a ladder structure. So this is the original structure, and the lump element will be connected in this manner. You get a pi level on the top. The left side of LC is a capacitor. I don't draw it here because both inductor have the same format, and as a result, the capacitor connected to the left end of each of the inductor LC will combine together at port 1. And the most important thing you need to know at this stage is to calculate LC and CC. If you calculate this, you just use the impedance divided by omega. The characteristic impedance of this one, VQ, is equal to square root of 2 times V0 and divided by omega. And for C of C is 1 over omega, and the characteristic impedance. Characteristic impedance is square root of 2 times V0. So that's all. That's all you need to know. Then you can even extend it to Y bound, broadband. Alright, you just add a few more sections here. Okay, let's take a look at another version of multi-way power divider. Previously, I have already shown you the most basic form of power divider, where you have one input and two output. And previously, let me show you. You can use this power divider to deliver power to two identical isometric antenna, or even non-isometric antenna, and this will end up with an antenna array, and the voltage will be synchronized. And this is how we drive antenna array. But antenna arrays mostly have more than two elements. So this is why Wilkinson power divider are so useful. So in this case, you're delivering the power to multiple output. So in action with this device, you can deliver power to multiple antennas, and this is essentially a system of n element antenna array. And there could be a way to modify the resistor, in a way to deliver unequal power to a non-regular antenna array. Say, for example, binomial array. You can do that. And one thing you have to bear in mind, you have to be mindful. The quarter-wave transformer would have different characteristic impedance. In this case, it will be square root of n times V naught. And this is the multi-wave power divider. And again, you can turn this power divider into lump element 1. It will work, particularly at low frequency. Okay, I'm talking about this page. Okay, in this case, this is the end of the slide. If you have further questions and you want me to address them, please tell me. Leave your comment in the comment section of this video. Whatever comment you have, you will help. Thank you.